Thank you, Christian. Yeah. Good morning. As Christian said, I will present the concepts and the overall architecture for the CoSSMic project. The motivation. So locally deployed PV panels is an important element in zero-emission buildings and in the transition to a future energy supply system based on renewable energy sources like the solar power. But the output from the PV panels has fluctuating nature due to the fluctuating insolation. So here, this curve shows the output from the PV panels. So in a clear day, the curve is smooth, but in a cloudy day, it is highly fluctuating. And so this limits the predictability of the power production. In addition, there is a time mismatch between the generation and the consumption of the power. The PV panels produce energies during the day, but the people tend to use the energy in the evening after they come back from the work. Therefore, local storage capacities is important and useful to cope with the fluctuation of the solar power output and the mismatch between the time difference between the production and the consumption. However, the batteries are expensive. So nowadays, with the popularity and availability of the electric vehicles, the batteries of parked and charging electric vehicles can be used as mobile and additional storage capacities. So in addition, different buildings have different energy needs and the use patterns. So if we can coordinate the energy consumption patterns and the use of storage capacities in the neighborhood and adapt the usage patterns to the situation, then we can absorb the fluctuation with less total storage capacity and reduce the demand of the central power grid and reduce the demand for the carbon-based backup power generation capacity. So the CoSSMic approach is to exploit the variation in the energy consumption patterns between the buildings in the neighborhood by coordinating the load shifting and the use of storage capacities in order to maximize the self-consumption of the locally produced PV power in the neighborhood. So we can see there is a microgrid. A microgrid is usually confined in a smart home or office building and embeds the local generation and production of the solar power and the number of power consuming devices. In addition, there are also electric vehicles connecting and disconnecting dynamically, representing a dynamically varying storage capacity. So the CoSSMic project will develop an innovative automatic ICT-based system to coordinate the power generation, consumption, and storage of the microgrids in the neighborhood on users' behalf, and according to the rules and the constraints set by the house inhabitants. In addition, CoSSMic will propose suitable business models, both for sharing the benefits between the members of the neighborhood and the trading of power with the public power grid. So here are the main concepts in the CoSSMic project. We have a household. A household is a building, a part of a building or a group of buildings. These households will form a neighborhood with an agreement to coordinate the management of their energy consumption and the use of production and storage facilities. The households have different devices. Some devices are power-consuming devices like the washing machine, dishwashers, air conditioners, etc. And there are also power generation and storage devices. So households are connected to the public power grid, and they have contracts with the DSOs, the distributed system operator, and retailers for this contract for delivery of power when local generation is insufficient, and also to allow the feed-in of excessive energies to the grid. So such connection is usually through a smart meter. So the key idea of the CoSSMic project is to facilitate the creation and operation of such neighborhoods by providing an ICT-based system that coordinates the timing of the energy-consuming tasks, which is also called load shifting. And this load shifting will be done according to the constraints and preferences set by the user. For example, instead of just starting the dishwasher after dinner, the user may just ready the machine and tells the system that the dishwasher should be finished before the dinner time next day, and then the system will coordinate the exact scheduling of this task with other energy-consuming tasks in the neighborhood planned in the same way, and also with the local PV production. And for price models, the retailers already offer some price models that vary over the day according to the feedback from the online markets where they buy their energy. But currently, such price models are usually static and predefined. And so in the future, dynamic price models with real-time information through internet will become more and more popular and more common. So CoSSMic will exploit these different price models. And also the weather has significant influence both through its effect on the energy production of the PV panels and also by determining the need for heating and cooling of the houses. So CoSSMic will use the weather forecasts to predict these effects. And currently, some weather forecast services are available, so we can use them. So the CoSSMic system consists of a controller in each building or each household. So these controllers are microcomputers like the Raspberry Pi. And such controllers can collect the data from the devices in the household and also send control information to the devices. And these controllers will communicate with the controllers in other houses in the neighborhood through the house Wi-Fi and internet. And the user will interact with the system using smartphones and touchpads connected through the internet. So the CoSSMic system is peer-to-peer, has a peer-to-peer architecture. So there is no central controller in the neighborhood. This peer-to-peer system is based on multi-agent systems where the software agents in each household represents the user and implement energy negotiation and distributed task scheduling. And the CoSSMic aims at low threshold technology. So we adopt low cost hardware like the Raspberry Pi, these microcomputers, and we also utilize the existing communication technologies like the internet and Wi-Fi. And then we will ensure that the software is easy to install and use. And then the system will have a flexible configuration. For example, the software components should be deployable locally or in the cloud. And finally, the CoSSMic software is open source. So they are executable on common available hardware and are downloadable from an open access open source site. So we have developed the overall architecture for the technical solutions as depicted in this figure. So the prediction component computes the forecasts for the PV production and their prices for the electric power exchange with the public grid. They're based on the third-party services and knowledge about the house and its PV installation. For example, the weather services can be used to predict the irradiation on the solar panels and the heat exchange of the house with the environment. And we have this task manager component. It is the master agent of the multi-agent system, and for the negotiating or the load scheduling, and it has several responsibilities. It will create consumer and the producer agents to represent the consumer and the producer devices in the household. And it manages a list of planned tasks for the household and provides the task planning interface to the user interface software to allow the user to create, plan, and replan the tasks with the associated constraints and preferences. And also, it will abstract the tasks into more or less shiftable loads and hands them to the appropriate consumer agent. And it also receives predictions from the prediction component and forward them to the producer agent. The consumer agent negotiates the power delivery agreement with the producer agents of the whole neighborhood and scheduling of the loads with the other households and returns the scheduled loads. And the goal of the negotiation is to maximize the self-consumption of the locally produced PV power in the neighborhood. So negotiation and renegotiation is triggered when it receives a new load or there is a change to an already received load, or the prediction change. And the responsibility of the load controller is to execute the loads according to their schedule so that the total consumption production of the household stays as close as possible to the schedule. So it may interrupt and assume the interruptible tasks. And in addition, we have user neighborhood management components for the management of users and their responsibilities, and also the system installation and management components. And finally, we have this central data repository, which collects the data from all the trials and makes the data available for analysis and simulation as part of the evaluation of the project results. So because we have, as Christian said, we have 2 trial sites in the project, one in Constance here and another in Italy. So we have only 2 trial sites. This limits the conclusion we can draw. So therefore, we also have the simulation, and we will run simulation to increase the significance of the results. And currently, we have an initial prototype available with partial functionality. And we are working with a complete version with all the functionality and the distributed negotiation and task scheduling. So this complete version will be used in the trials started in September. So more details will be given afterwards. So thank you. Yeah. Okay.